so here's where we were last time. We were talking about linear transformations, and thank you. So a linear transformation is a new kind of object that we hadn't seen before yesterday. It's a kind of a function that has certain key properties. And the reason we talked about linear transformations, I kind of hinted at the beginning of that discussion, which is it's going to turn out that when we talk about multivariable derivatives, really the best, most natural way to talk about multivariable derivatives is as a linear transformation. So the details of that will come along soon, not today, early next week would be my best guess. So anyway, linear transformations are going to be very important in this course. So the topic we're going to start with today of matrices is a convenient notation for representing linear transformations. And here's the idea. So here's a linear transformation. In fact, this is a function that we checked last time directly. The brute force, we confirmed that this is a linear transformation. Okay, so it plays nice with vector addition, and it plays nice with scalar vector multiplication. All right. We observed last time that if you know the image of E1 and the image of E2, in other words, if you know the images of the standard basis vectors, then knowing simply that it is a linear transformation tells you everything you should need to know. In other words, the information I have circled in purple communicates all the same information that I have circled in blue. Just knowing those standard basis vectors and that it is linear. So specifically, you just need to know what are these images. If I tell you what the images of those standard basis vectors are, then that tells you the entire linear transformation. So the idea then is that, well, let's just write those down in a compact, efficient form, like so. I'm going to make the first vector, the image of the first standard basis vector, I'm going to make that the first column of this little array of numbers. And the second vector, this image of the second standard basis vector, I'm going to make that the second column of this little array that I'm writing down here of numbers. And everything I could possibly want to know about the linear transformation is contained in that. Right? I know what the image of the first standard basis vector is. I know what the image of the second standard basis vector is. I know it's linear, and therefore I can deduce the value of any of the values of the linear transformation. So why write this? There's just more to write down. Right? Everything, all the critical information is there. Okay, so that's why I say that. So we're going to call this a matrix, and that's why I say that this is a shorthand for a linear transformation. It is a very compact, efficient way to write down all the information that is otherwise represented in a linear transformation. Okay. All right. Some of y'all might have seen matrices before. There are different points of view you can take on what is a matrix and why do we write a matrix that way, etc. This is my favorite one. And it's going to allow us to motivate some of the formulas that y'all might have seen. So, for example, how many people have seen how to multiply matrices? Okay, a few of you have. Of y'all, how many know why that's the formula for multiplying matrices, or have any sense of why that's anything other than just a super weird arbitrary formula? Right, exactly. Of course not. Right. So this kind of thing doesn't get covered in high school classes. But we're going to be able to see that today. And it turns out there's a very simple and natural answer to the question. All right, so here's our definition. Definition of a matrix representing a linear transformation. It's an array where the columns of the matrix are the, I'll do this in yellow, the images by the linear transformation of the standard basis vectors. So the columns are the images of the standard basis vectors. Just like I did here, just like I did in that previous example. Okay. So it's a good thing to make sure to remember. In fact, this little phrase right here, the columns are the images of the standard basis vector, is very, very handy to remember. We're going to make use of this in a couple instances in this course and many, many times in Math 216. Okay, so here's an example. Just one more example. You've already seen one, of course, but here is a linear transformation. You can confirm for yourself that this is a linear transformation straight from the definition. And so how else might I write this? Well, I can write it in matrix form by plugging in one at a time the standard basis vectors into there and see what vectors come out. And these images, the outputs, end up being those three vectors. Those then are what go into defining the matrix. So there it is. Plug and chug. Is everybody on board? All right. Let's turn it around backwards. Suppose somebody gives you this matrix and wants to know, what's the linear transformation that this represents? Well, again, it's just a matter of sort of translating in the opposite direction. The point here is that this represents a linear transformation by its columns telling you the images of the standard basis vectors. So from that information, how can you deduce what the linear transformation is? How can I compute t of x? Well, t of x is going to be found by taking the appropriate linear combination using the coordinates of x of those given images of the standard basis vector. So this is that linearity property that we talked about last time. And again, since we know those images, we can do this calculation like so, and then multiply, collect terms, and there's your linear transformation. That's how you compute t of x. So, one-to-one correspondence there. Okay, all right. So that's how to think of a matrix as a shorthand for a linear transformation. Now I want to talk about how to think of a matrix as an algebraic object. So as it is, it's just a shorthand, right? But we need to be able to interpret, it's awfully convenient as it turns out, to be able to interpret a matrix as an algebraic object where you can do operations with it. So for example, how would I multiply a matrix times a vector? As it stands, there is no such operation. We'd like to build such an operation for algebraic convenience. Now, as with all situations we've found ourselves in where we have a new operation to talk about, we think back to the very first instance when we talked about how to add vectors. How should we add vectors? What do we want vector addition to mean? And we came up with a reasonable, sort of geometrically, physically natural answer to that question, and then we made our definition accordingly. So I'm going to do the same thing here. Let's ask the question, how should a matrix multiply times a vector? What should this mean? Well, keep in mind that matrix is supposed to be representing some linear transformation t. So really, because a matrix is representing a linear transformation, what a matrix does to a vector and what a linear transformation does to a vector, I kind of feel like they really ought to be the same thing. Because if a matrix is just a shorthand for that linear transformation, what else would it be? Right? So we're going to make this choice. I'm going to define matrix vector multiplication. Let me zoom in on this. I'm going to define matrix vector multiplication to be the vector that you get when you take the given vector x and the corresponding linear transformation t corresponding to the matrix you were given, and if you compute t of x. So that's going to be our first sort of point of view on matrix vector multiplication. We're going to define it to be what it should be. Okay. All right, and that's what I've written down here is interpretation 0. This is our sort of founding interpretation of what a matrix vector product ought to be. So, all right, now I don't want to have to tediously go through this process every time I want to multiply a matrix times a vector. I don't want to have to deduce what is that linear transformation and plug the vector into the linear transformation and then get the conclusion. I'd like to have some really convenient, efficient little numerical algorithm for how to compute this. So that's what we're going to do now. It turns out there's a wonderfully convenient one, and here's the way we're going to do it. Whatever matrix you're interested in, multiplying by a vector, that matrix is going to have certain columns. Let's give those a name. Let's call them A1 through AN. Pretty common notation, by the way, in situations like this to use a lowercase to represent column vectors. And the subscripts indicate which of the several column vectors. Okay. And if I want to multiply that by a vector x with coordinates x1 through xn, well, how does this work out? Well, keep in mind, based on our interpretation 0 here, I need for this product, I need that to equal to t of x. But t of x, if you look at this little calculation here, t of x being as it is a linear combination of standard basis vectors, I can rewrite like this. These standard basis images, I'm running out of colors again. The images of the standard basis vectors are those column vectors. Column vectors in the matrix. This, what I have highlighted in red here, is in fact just the definition of our matrix notation, right? Images of the standard basis vectors are those column vectors. So what we end up with then, I didn't want to erase that, sorry. Altogether, what we end up with is that this matrix vector product is a linear combination of those column vectors, where I use the coefficients of the vector, the object vector, as my coefficients. So let me zoom in on this for a second. If you want to multiply a matrix times a vector, if that matrix is going to represent a linear transformation and if linearity is going to be respected, AX has to be, and again, I've got it highlighted here, it's a linear combination, you can see right here, it's a linear combination of those column vectors, and the coefficients in that linear combination are the coordinates of the vector. Okay. So, in case you were ever wondering, why is it that we multiply matrix times a vector in that way? This is why. Okay. Now, there's a more common way to think about matrix vector multiplication that perhaps more likely y'all would have seen in a high school course, and that is to ask the question, okay, well, look, suppose I want to compute this product, but I want to compute it one entry at a time. What colors am I using for? Oh, I've already erased them. Oh, well. So I want to compute, let's say, just that entry. Let me make that a box. It looks like a 0. I want to compute just the first entry of that matrix vector product. Well, I know it's the vector itself is this linear combination. So if I'm taking a linear combination of these vectors using these numbers as coefficients, and if I want just that first entry, well, that first entry in that linear combination is going to be the linear combination of the first entries in those vectors. I mean, just think about how you multiply and add vectors. Scalar vector multiplication and vector addition is all done component-wise. It's all just, each component is dealt with separately. So if I want to know the first component, the first entry in this linear combination, I just take the same linear combination of those first entries. And now, kind of a silly observation here, though. Think about it. A linear combination of a bunch of numbers is a dot product. Right? Like so. So this may be the point of view that was given to you on matrix vector multiplication in high school or wherever it was. That the way you multiply a matrix times a vector is you look at the row vectors And each row vector, you do a dot product with x to get then one entry of the product one at a time. So in case you were wondering, again, where did they come up with that formula? Why is that why we multiply a matrix times a vector? Well, because this is what it has to be to give us this linear combination formula. And this linear combination formula, it has to be in order to respect linearity, in order for the matrix to actually represent a linear transformation, as we started off motivated. So there you go. All right. Okay, so now which should you use if you want to multiply a matrix times a vector? Or let me say that a bit more broadly. How should you think of matrix vector multiplication? Well, there's some pros and cons here. If you think of it as a linear combination of column vectors, there's certain pros and cons. If you think of it as a vector whose entries are dot products, certain pros and cons. The advantage of thinking of it as dot products is arithmetically, in terms of how you write it down on the page, it's probably a little faster, a little bit arithmetically quicker. If you think of it as a linear combination of column vectors, interestingly, it turns out there's some really powerful interpretation advantages to this. A lot of those you'll see in Math 216. But various places here and there, and we'll see some in Math 212 as well. So you need to understand both of these points of view. There are conceptual advantages to this linear combination point of view that you can't get from this. So if you say, phooey on linear combinations, I'm going to just do it this way, arithmetically you'll be fine. But that's not what we're going to be doing, entirely. In this class and in Math 216 and in future classes, your job is not to compute numbers. They got computers for that. Your job is to understand how ideas relate to each other. And this point of view is very important in that sense. So please don't fall for the mistaken point of view of, I'll just do it this way. It doesn't work. Okay. All right. So here's a couple of examples. In fact, here's the same example twice from different points of view. Matrix vector. And here's how I do the matrix vector product as a linear combination. You'll notice linear combination of the column vectors where I use the coefficients, the coordinates of the vector as coefficients in that linear combination. So straight out from our interpretation number 1, take that linear combination and that gives you this matrix vector product. Now that same calculation you could achieve instead by looking at the row vectors of the matrix and each row vector of the matrix gets dotted with that one input vector. And you'll note it gives you the same answer. So arithmetically, these are equivalent. Conceptually, they're significantly different. Okay. All right. Next thing I want to be able to talk about, how do I add vectors? How do I add matrices? Well, again, we could just make something up. We could just write something down. It's arbitrary and pointless. We want to know why something should be a certain way. So the idea here, I'm going to base our motivation of matrix addition on how linear transformations add. And linear transformations, being functions, should add as functions. And this is how you add functions. The sum of two functions is a function which, when you evaluate it, gives you the sum of the two values of the function. I mean, what else would it be? Right? It sort of has to be. So you've seen examples of adding functions like this in single-variable calculus classes, talking about properties of integrals and that kind of thing. Okay. So that being the case, I'm going to define the sum of two matrices to be the matrix that represents what we already have as a sum of two linear transformations. Again, we kind of have to. What would be the the only reasonable choice to make if you know how to add linear transformations, and if linear transformations are represented by matrices, adding matrices ought to be corresponding to adding linear transformations. Okay. All right. So, computationally, how do I do that? Well, don't forget the way matrices represent linear transformations is like this. The columns of the matrix are the images of the standard basis vectors. That's our definition of a matrix. The columns are the images of the standard basis vectors. We just agreed on the previous page that this is how you add linear transformations. This is what T plus S means. T plus S is a linear transformation such that when you evaluate it, you get the sum of the values of the, again, from before. And previously, well, I'll say it this way. This linear transformation is represented by some matrix, and this linear transformation is represented by some matrix. And so what we have then is a handy formula for how to add two matrices. One last step here. Columns of a matrix are the images of the standard basis vectors. So having made that last step, look at our final formula. A column of the sum of two matrices is the sum of the two corresponding columns of the original matrices. So in other words, you add matrices one column at a time. The columns are vectors. We know how to add vectors. So add the columns one column at a time. Now, side note, how do we add vectors? One entry at a time. So the punchline then is that if you have two matrices that you want to add, here's how you add them. One entry at a time. So that plus that gives me that, for example. So the good news here is that this is the formula. If we had sort of naively, without any perspective or motivation, just written down an arbitrary formula for how to add two matrices, we probably would have written this down. This is really good news as an answer, right? But I think it's important to note that this formula is not just convenient and arbitrary. This formula is what you get by insisting that the way we add matrices has to correspond to adding linear transformations, because matrices represent linear transformations. So this is not just convenient down here. This is natural. Okay. All right, so a quick and easy example if you want to add these two matrices. One entry at a time. Let you guys check the details. I'm going to leave it to y'all to read through the next part that I did in parallel here, and that is that if you have a matrix and you want to multiply that matrix times a scalar C, then you do that one entry at a time as well. Now, again, if you were to naively and blindly arbitrarily write down a definition of scalar matrix multiplication, yeah, you probably would have written that down. It's convenient. It's notationally, dare I say, expected, right? But again, not the point. The point is that this is natural. This corresponds to multiplying a scalar times a matrix by multiplying a scalar times that corresponding linear transformation. So I'll let you guys read the details. It's a lot like the addition argument that we just walked through. Okay, now here's where we get to matrix multiplication. The punchline here is going to be different than what those of you who have seen matrix multiplication before. Well, let me say that differently. The result we're going to get here is not going to be expected. It's not notationally expected or natural. It's pretty weird, really. The punchline formula we're going to get for how to multiply two matrices is weird. But there is a very natural motivation for it. And so ultimately, the way we multiply matrices really has to be that way. It's not just a weirdo made-up formula that, it really sort of has to be that way. And we're going to motivate that by making the observation that, look, if you have a vector, let me come down here and I'm going to highlight this formula. If you have some vector, and if you apply a linear transformation T, and then subsequently, which by the way is done by multiplication by some matrix A. And then subsequently apply some linear transformation S, which of course is going to be accomplished by multiplying by some matrix B. Altogether, what you've done is you've effectively applied this composition, S compose T, to that vector. That's going to be represented by some matrix, composition of two linear transformations. This is a linear transformation. It's going to be represented by some matrix. And if you think about it, this kind of has to be the product B times A. Because, I mean, look how the algebra works out. I need, for this matrix C, to be the same as first multiplying by A and then multiplying by B. And if I want this matrix multiplication to be associative like that, I don't have any other choices. Right? If I want BAX to equal to B times AX, gosh, I really hope that, I mean, it's super weird to think about that possibly not being true. It leaves us no choices. The matrix representing a composition of linear transformations has to be my definition, my choice for what it would mean to multiply two matrices. Certainly, it's a very natural choice to make. It's a highly desirable choice in that it gives us this associativity. Okay, so that being said, now that we have a motivation, how do we actually come up with our formula? Well, we have to set up a little bit of notation. Again, one matrix at a time. Let's look at the matrix A. I need to be able to talk about its row vectors, but I'm also going to need to be able to talk about its column vectors. So I'm going to give these this notation. I'm going to use, as I have before, lowercase letters to represent column vectors. I'm going to use capital letters to represent row vectors. Likewise for the B matrix, capitals for the rows, lowercase for the columns. Okay. And now let's just walk through and see what our product has to be. Again, don't forget, and this is our sort of definition of a matrix. The columns are the images of the standard basis vectors. Our interpretation 0, our motivation for what BA ought to be, is that it has to represent that composition, S compose T. Here's how you compose. Composing says you first do T, and then afterwards, whatever comes out, you do S to it. Okay. T is accomplished by multiplication by some matrix, I'm going to call it A. That's this matrix up here. S is accomplished by multiplication by this matrix B. And good news, I already know what that is. I already know what it means to multiply a matrix A times a standard basis vector, or in fact any vector. And again, the columns are the images of the standard basis vectors. So A times a standard basis vector EJ is AJ. That jth column of the A matrix. So here's our kind of punchline, and that is that if you want to multiply two matrices, want to multiply B times A, the way you're going to do it is one column at a time. The columns of that product are the matrix B times the corresponding columns of the A matrix. That's kind of what it has to be. So one way you can think of matrix multiplication, if you want to multiply a matrix times another matrix, is you can compute one column at a time, and in particular just take the left matrix and multiply by the corresponding columns, the corresponding column of the right matrix. Okay. And side note, let's not forget we have an interpretation of this already. How do you multiply a matrix times a vector? Well, this is a linear combination of the columns of the matrix, where I use the entries of this vector as my coefficients. So linear combination of these columns using those as coefficients. Okay. So altogether, that gives us this interpretation 1. This matrix vector product Baj is a linear combination of the columns of B where I use the corresponding column of A as my coefficients. Column of the product. Let me highlight that also. Okay. Columns of the product have to be these matrix vector products. These matrix vector products are linear combinations of the columns of B. I use this vector as my corresponding coefficients. Okay. All right. So let me show you an example. I'm going to skip down here to where I compute one of these. Let's compute this product. What I've argued is that I can compute that product one column at a time. Let's compute the first column. How am I going to compute this first column? Well, that first column is going to be a linear combination of the columns of the left matrix, where I use, now I'm computing the first column here, so I'm going to use the first column of the right matrix as my coefficients. So, compute that first column. These are the objects in play. Take the linear combination and get that result, which I can put there. Yeah?
In order to multiply matrix, do they have to be the same size?
They have to have something in common. In particular, the number of columns of the left matrix that you're going to be taking a linear combination of has to equal to the number of entries in a column of the right matrix, so that you'll have the right number of coefficients to match the right number of vectors. Said differently, the number of columns of the left matrix has to equal to the number of rows of the right matrix. Yeah. So there's different ways to think about this requirement. That's a great question, by the way. For the moment, since this is the only formula we have for the product, I'm going to motivate it like this, that the number of coefficients and the number of vectors that you're doing in a linear combination that have to kind of fit together. Yeah. Right. Okay, now if I wanted to compute the other column, how would I compute that second column? Well, I would do that second column by using the second column of the right matrix as my coefficients. Still the same columns of the left matrix, just now I have these other numbers as coefficients, multiply and add, and that gives you that second column. Anybody see how the process works? It's kind of a mechanical process. Okay. Now there's a twist on this. It's not hard to motivate. We've already kind of seen that I could interpret a matrix vector product a little bit differently. I can interpret this B times AJ, instead of as a linear combinations of the columns of B, I can interpret it as a bunch of dot products with the rows of B. Right? That was the other formula that we had for that. So, well, that gives us a different notion of matrix vector multiplication. Excuse me, of matrix multiplication. So specifically, I can compute the product one entry at a time, taking the corresponding row of B and dot producting it with this corresponding column of A. Okay. So this is the point of view that a lot of y'all might have, or more likely have seen on matrix vector multiplication. So this is not a column at a time or a row at a time. This is one entry at a time. And so, for example, how would I compute that entry? Well, I would take the corresponding row of the left matrix. I would take the corresponding column of the right matrix, and I would do this dot product to get that number. And then you do that for each entry. Now, again, suppose you like this one better. And by the way, this one has the nice advantage that you can really kind of just write down the numbers one at a time. I mean, this 31, you don't have to write this big middle part. You can just eyeball over here 1 times 7 plus 3 times 8. Just kind of a, this little process. And write the numbers down one at a time. Arguably, you can do it with as little pencil lead as possible. And that's nice. That's appealing in a certain way. Again, keep in mind, your job is not to be a computer, right? You can't compete with computers. You should try to distinguish yourself in a different way, right? You're more useful to an employer doing something other than being a really slow, expensive version of Wolfram Alpha, right? So, more important than what's computationally convenient is where are the ideas? What connects to what? And while this is a useful point of view, and we are going to see some applications, some situations where thinking of a matrix product as a bunch of dot products is useful, it is also useful, importantly useful, to think of a matrix vector product as columns that are linear combinations of these columns using those numbers as coefficients. Okay. All right. So last one, and now this is just a formula that works out nicely, but you can instead think of matrix multiplication as a linear combination of rows. And you can just kind of think through how the arithmetic works out of a dot product, thinking about it kind of backwards. I don't want to go through those details, but here's the punchline. Yeah, here we go. I can compute the rows of the product one at a time as linear combinations of the rows of the right matrix, where you use the corresponding row of the left matrix as your coefficients. So that is another way to get the product, not one column at a time, not one entry at a time, but one row at a time. You do have to keep straight which way it goes. If you're computing rows, you're looking at linear combinations of the rows of the right matrix. If you're doing it one column at a time, you're taking linear combinations of the columns of the left matrix. So make sure to get it straight. This row point of view also really useful, especially when you get to Math 216. It's going to turn out to be indispensably valuable. So good thing for you all to keep in mind who will go on to 216. Okay, so we've got a definition of what a matrix is. It's a shorthand for a linear transformation. We've got various algebraic constructions, how to add them, how to multiply by scalars, how to multiply them by vectors, how to multiply them by each other. And all of these operations we have motivated conveniently all by the fact that we want them to make sense being thought of as representing linear transformations. So not only do matrices represent linear transformations, but matrix operations represent linear transformation operations in natural corresponding ways. Okay, I'm going to let you all read this little theorem for yourselves. It's pretty straightforward. Okay, so done with chapter 3. Side note, very quickly, what I've told you all about linear algebra, this little 2-section micro chapter on linear algebra is the tip of the iceberg. Right? There's much more to know about linear algebra. If you are an engineer, and you will see that in Math 216. If you are not an engineer, if you are an econ major or something like that, let me point out, linear algebra is really, really useful in lots of ways. Linear algebra is useful in way more majors than require it. Right? So even if your major doesn't require it, you might still consider the possibility of taking a linear algebra course. And Math 216 is a nice choice, certain pros and cons. Math 221 is really a stronger choice for linear algebra, and I would encourage you to consider possibly maybe taking Math 221 if you want to get a really robust introduction to linear algebra. Okay. All right, so moving along, we're going to talk about derivatives now. Side notes, here we are late in the second week, and we're finally going to get around to doing a little bit of calculus in a multivariable calculus course. So it seems a little bit of a late entry, but we've got all of our groundwork set up now and all the tools that we're going to need to do to be able to do multivariable calculus in a really significant way. Nevertheless, kind of exciting as our first venture into multivariable derivatives. I do want to say, I want to segue into the multivariable calculus by starting off reminding you about single variable calculus very, very briefly. I know that you all know single variable calculus. Just a quick reminder. Don't forget there's this formula here. It gets written in different ways. But you can think of this as a formula for linearly approximating a function. This is the motivation for the formula for the tangent line to a curve. So, again, written in different ways. But hopefully this looks familiar to everyone. I'm going to rewrite this a little bit by taking that and moving it over to the other side and viewing the resulting difference as change in f. Right, and we can reinterpret this then as saying that the change in f is approximated by the derivative times the change in x. Right, a different twist on an old fact. You might have even seen it written like this at some point. Another little quick flashback. The chain rule. Everybody remember the chain rule? This is the Leibniz notation version of the chain rule. Everyone likes to do that as a kind of a way of motivating what's going on. There's little formality problems with that. But in a single variable context, that's victimless crime. Okay. So what we have here then are two arguably, seemingly maybe different applications of the derivative. And I'd like to point out that these two interpretations of the derivative actually do have a lot in common. In both cases, we're interpreting the derivative as being something that you do to some sort of a change in x. Now, in the first case, it's a discrete change in x. I consider what happens if x starts here and ends there. If x jumps from there to there all at once, discrete change in x. Here, I'm talking about a rate of change of x. Nevertheless, in both cases, we're talking about x changing in different ways. And the derivative is the thing that helps you convert that into a corresponding kind of change in the function. So in both cases, the derivative relates input changes to output changes. And I think this is a really important point of view on derivatives. There's different ways that you can talk about derivatives, and I know a lot of y'all might most fundamentally think of derivatives as slopes of tangent lines to graphs, right? And that's certainly the way it was introduced to me the first time, and that's in a single variable context. It's geometrically appealing, and that's nice. And it's a good point of view. I don't mean to detract from that point of view, but I think it's very important not to cling to that point of view of derivatives as being slopes of tangent lines. That's one of many applications. Really, more fundamentally, the derivative is a relationship between input changes and output changes. And so that's the big point of this little quick subsection is I want you to start thinking of derivatives that way. Be prepared for the fact that we're going to need this point of view when we start talking about multivariable derivatives. Okay. All right, here's a couple of quick examples. And I'm not going to go through the details of these examples because these are really straight out of single variable calculus. But you can compute an output change approximation anyway from an input change by multiplying by the derivative. Or you can compute an output rate from an input rate by multiplying by the derivative. So scan through these examples, remind yourself of these applications of single variable calculus, and these are the points of view on those derivatives that I want to take in this course. Okay. All right, fine. Now, for the moment, in single variable calculus, the changes that we were looking at here, changes in the input, changes in the output, they were numbers. How fast is x changing? It's just a number representing a rate. That's all it is. Let me point out that I could think of those as vectors. Seemingly a little bit silly, I suppose, but if the input x is moving with a certain speed, I could think of that as a speed moving in a certain direction, and therefore a magnitude in a direction, and therefore as a vector. Right? Again, the pointlessness of this seems to come to the fact that, well, what direction would it be going? There's only one direction. It's a one-dimensional domain. There's only one direction. So why interpret it as a vector? Again, we're laying groundwork for generalizing to a multivariable context where we're really going to have to talk about directions. So it's valuable to, again, extend your point of view on single variable derivatives as a relationship between input vectors and output vectors. Here, those input and output vectors are representing velocities, rates of change in this one-dimensional case. In this picture over here, input vector, output vector, they're representing changes, displacements, I guess you might say, even though those displacements are in one direction and they're just numbers. But we can think of them as being vectors. Okay. Lastly, of course, these pictures are being drawn in the graph context. We've seen many examples where graphs, great though they are in single variable, don't work out well in certain multivariable functions. Even something as innocent as a function with two inputs and two outputs, it's a four-dimensional picture. We can't begin to draw it. It's out of the question. So I don't want our point of view on derivatives to be dependent on this graph construction. It's dimensionally wasteful and awkward. So I'm just going to redraw these pictures in this other way, where so here's the displacement point of view on derivative. The derivative is the relationship between this input change vector and that output change vector. Same picture as on the previous page, I just didn't draw it as a graph. Nevertheless, there's an input change, there's an output change. I don't need that graph picture. And then likewise here, relationship between input velocity and output velocity. The inputs are in the domain, the outputs are in the target. We don't need the graph picture. Okay, so what I've done now in this 10 minutes that I've been talking about single variable calculus is all I've done is take old ideas and sort of tweak them around to a point of view that I claim is going to be really useful for us, right? As we try to extend the idea of a derivative into a multivariable setting. So hopefully not that many new ideas have hit you here in the past 10 minutes. But I do want you to go to the trouble of working with me, bear with me to think about this change in perspective on these old ideas and have yourself oriented, prepared to think about derivatives in these ways. Derivatives are things that you do to relate input vectors to output vectors. All right, so that's all I'm going to say about 4.1. Let's go on and do 4.2. Should be fine here. So we're going to talk about derivatives of parametric curves. Actually, this is going to be surprisingly convenient to define derivatives of parametric curves. We're going to use this more as a tool for other more sophisticated constructions a little bit later on. But taking a derivative of a parametric curve, not that big of a deal. Here's a parametric curve. Position's a function of time. So position is given by several coordinates in the target. Time is your input variable. So position's a function of time. Okay. So let me take a wild stab at it, at what maybe I might want to define to be my derivative of such a function. Let's just write down the old Math 111L formula for derivative. And hopefully this makes sense. I don't know, for lack of anything else to try at the moment, let's just see how this works out. And what's super convenient is it works out just fine. It actually works out very nicely. And so we're going to go with it because it's convenient and it works out and it's familiar. So specifically, the derivative, classical notation, right? You've all seen this notation before. And it's a limit, sure. It's a limit of change in the output, that's a vector displacement in this case, divided by change in the input, which is the difference between the time, sort of the start time t and the end time t plus h involved in that displacement. Okay. So, just like the definition of single variable derivative. How would I compute these things? Now, there is a scary thought before us, and that is that all of the old rules that we knew for how to compute single variable derivatives, in fact, you might recall this formula gets jettisoned pretty fast in a single variable calculus course, and then you start taking derivatives with the power rule, and the derivative of sine is cosine, and then there's a chain rule, and a product rule, and a quotient rule, and you hardly ever go back and actually use this. Right? So, the problem, though, is all of the old single variable calculus rules only apply to how to take derivatives of single variable calculus functions. And this is a vector-valued parametric curve, and it's different. So there's a concern that maybe we have to we might have to come up with a whole new set of shortcut formulas for how to compute derivatives of these kinds of functions. That's a fear that we should be worried about. The good news is we don't. It works out wonderfully conveniently that if you want to take a derivative of a parametric curve using that definition, you can plug into that definition, go through a certain amount of algebraic arguments, and the punchline is that that parametric derivative is computed with good old single variable derivatives, one component at a time. So you just go up to the individual component functions and take their single variable derivatives separately. Oh, gosh, I have a typo in here. Sorry about that. I put little vector hats over that. I don't know why. Let me erase those. There we go. Good old single variable derivatives. One at a time. Couldn't ask for a nicer answer. And it works out. Now, I'm going to leave it as an exercise for you guys to follow through the algebra. All that's happening, maybe that's a little too much. All that's happening in this algebra is we're making the observation that everything that goes into this construction is computed one component at a time. So, specifically, how do I subtract two vectors? Well, I subtract vectors by subtracting one component at a time. Right? How do I divide a vector by a scalar? Well, I divide a vector by a scalar by doing one component at a time, by dividing each individual component by that scalar. How do I compute limits of multivariable? I guess I'm going to go through this with you. How do I compute a limit of a vector valued function? Well, the definition that we made back in a couple sections back, is that those limits are computed one component at a time, and these are these single variable derivatives. Nice fact, a really nice fact. It saves us having to rederive a bunch of different formulas for how to compute these parametric derivatives. Okay. Now, what remains, and what you might be sort of worried about right now, is the question of, is this at all useful? Like when we wrote this down in a single variable calculus class, we had a particular geometric application in mind. How do I compute slope of a tangent line? And the answer to the question of how to compute slope of a tangent line ended up being this. That makes this formula in the single variable context geometrically natural. I have given you no such geometric interpretation at this point. I wrote down a formula out of laziness, right? I don't know anything else to try. Let's write this down. I've showed that it's algebraically convenient. So what? It still remains to be seen that this definition has anything to do with anything. Right? It's not just some little made-up little silly formula. So that's what I want to talk about next. I want to persuade you that this is geometrically natural. So I'm going to come up to this picture, and let's think about the objects in that definition. So there's R of t, that's sort of the starting point. Here's R of t plus h, that's sort of an ending point. So this difference, the numerator in our expression, is that vector. It's what we're going to call a secant vector. So it's a vector from one point on the parametric curve to a nearby point on the parametric curve. Okay. Now we know we're going to be taking a limit, right? So these points are going to be getting closer and closer to each other as this h gets smaller and smaller. And t plus h are more and more nearly kind of close. They're almost exactly the same time. And so these points are going to be getting closer and closer. So this difference vector, that's a secant vector, is going to be becoming more and more like a tangent vector. It's not actually a tangent vector. It's never actually quite a tangent vector, but it gets closer and closer. So in the limit, not hard to persuade yourself that this is a tangent vector. So there's that. Now let's talk about what's the magnitude of the derivative. Oh, the magnitude. I'm going to skip a little bit of formality, scoop it under the rug. It's not Math 212 appropriate. But if I want to take the magnitude, I can take the magnitude of the numerator and divide by the magnitude of the denominator. And these both have natural geometric interpretations. The magnitude of that displacement vector, the magnitude of this vector is distance. Well, not exactly. I mean, the magnitude of the displacement vector is a sort of as the crow flies distance. We actually went along this curve, which is not exactly a straight line, but in the limit, as the distance as the h gets smaller and smaller, we're talking about a more and more nearly straight line distance across that displacement vector. So it's just the magnitude. The magnitude is just the distance traveled along the parametric curve. H, of course, is just time. H is the amount of elapsed time between the starting point t and the ending point t plus h. So what we've got there is an limit of distance divided by time, and that should be an old familiar physics concept. Distance divided by time is speed. Okay. So instantaneous speed. So I know two things about this derivative vector then. This derivative vector, dr dt, it's a tangent vector, for one thing. And secondly, it's a tangent vector whose magnitude is the speed of the parametric curve. In fact, that's exactly the definition of a velocity vector. Think about it, right? What is a velocity vector of a parametric curve? If you had a particle moving around in space, that particle, as it moves, is going to be moving in a certain direction, and it'll be moving with a certain speed in that direction, and that's how we define velocity. Weirdly, the parametric derivative gives you exactly that same vector. Tangent vector, in other words, a vector pointing in the direction of motion and where the magnitude is the speed. So this is a really nice interpretation. This kind of justifies our otherwise lazy choice here to just write down an old formula because I was familiar. Right? But writing down this old formula gives us something extremely physically natural, namely velocity vector. So I hope this might actually be slightly familiar. You all might remember that one of the things that you did with the derivative back in single variable calculus is to imagine scenarios where you have a car driving along a road and the car is moving with a certain speed, and you try to compute the speed, and you end up noticing weirdly that you get the derivative. Right? The same derivative that you initially motivated by trying to take a tangent line to a graph. So this is the same deal. Here we have a function representing position, and that's position. The derivative ends up then giving you the velocity. So arguably all we've done is generalize something from single variable calculus. Okay. All right, let's see an example. Suppose I have a position function for a bird. The bird's flying along this parametric curve. You might recall we studied this parametric curve back in Chapter 2. This is a parametric curve where the shadow is running around in a circle, but the height is doing this. So the bird is flying in a helix like that. And birds do this sometimes, by the way. You know, if they catch an updraft, you know, and they kind of fly along. So I don't know. Anyway, it's very physically natural. So a bird doing this on an updraft, let's ask the question, what's his velocity as a function of time? No problem. Velocity is a parametric derivative. So I just take the derivatives, one component at a time. One component at a time. These are easy single variable calculus problems. Done. Everybody happy? Okay. As with single variable calculus, you can turn these around backwards. Suppose instead of given position, can I find velocity? Suppose it's given velocity, can I sort of reverse engineer and find what the position function is? Well, you have to be given the velocity, but you also have to be given a starting point. Right, now you guys have seen single variable versions of this. And so this is the same thing, just in a multivariable sort of context. So given the velocity, if the velocity is the derivative of position, then position is the antiderivative of velocity. Okay. All right. So I just compute the antiderivative of that given velocity function. Antiderivatives are computed component-wise. Why? Well, because derivatives are computed component-wise. So you can just undo that. And these antiderivatives are pretty straightforward. These are, three separate little single variable calculus problems. Don't forget your constant of integration. That's a necessity. And you've got to have those integration constants because, well, in fact, when you take an antiderivative, you don't really know which one is the one that you need. So you have to leave that in there. Okay. And this is where your initial condition comes in. So that being the starting value, when t is equal to 0, that's what x is. This is what we've computed x to be. And this is the foot in the door that I need to figure out what these integration constants are. Now let me warn you about one thing, especially those of you who took single variable elsewhere before coming to Duke. A very common mistake, a mistake that I myself made on multiple occasions because no one really pointed it out to me when I was in high school. But you can't just let your initial values be your integration constants. It doesn't work out. Note, those numbers are not the same as those numbers. The initial values are not always the integration constants. Now, if your velocity function is given as a polynomial, then the antiderivative will be a polynomial. It'll be a polynomial where all the terms have a factor of t. When you plug in t equals 0, that will always be 0. And so in those cases, yeah, all of this turns into 0. And so it works out. But notice here, one of them isn't. Right? And that's why these numbers don't end up being equal to these numbers. And if you think about it in general, what possible general sense could you expect these functions to just magically, automatically, always equal to 0? Well, of course not. Not at all. Right? It's this weird coincidence that happens in introductory calculus courses because they happen to always choose functions where those happen to always equal to 0, and it's terribly misleading. Right? So please don't make that mistake. I do see this mistake in, even in Math 212 on a semi-regular basis. Students who never really quite thought the details of that through. So please don't make that mistake. Okay. Everybody see what I'm talking about there? Okay. Just like with single variable, if you're given acceleration as a function of time, you can anti-differentiate twice. You have to be given initial values and initial velocities in order to be able to work out the integration constants. I'll let you guys think through. It's the same as what we just did, but with 2 steps instead of 1. Morally equivalent. Okay. All right. So we have 9 minutes left. Well, 8 minutes left. I want to give you guys a preview of some of these homework exercises. There's a series of homework exercises that I have in here that are that actually cover a significant amount of material in a certain way. And so I want to walk you through the geometry. What's going on? What's the picture in these various exercises that you're going to be working out the details of on your own. So in particular, we're going to be studying a parametric curve. The first series of exercises y'all will be doing will be thinking about a parametric curve in the xy plane, and I have it drawn here. And our goal is going to be to try to get a handle on curvature. Right, so we know we can talk about slope, right? And we know that we can find the derivative of a parametric curve by looking at the velocity vector, or the velocity vector is computed by the derivative, and you can infer what the slope is in that way. But if you wanted to know what the curvature is, it's how much of this as opposed to that. There's this notion of how curved something is, and that's geometrically interesting. Okay. So how would we do that? So first, I have to make a definition of what exactly is this curvature thing. There's different ways that you can define it. The way I'm going to define it here is that we're going to look at this angle. I'm going to use phi, which is not a rare choice. It has the disadvantage of it looks like the spherical angle. Phi, it's not. It's got nothing to do with spherical coordinates. And then we're going to look at this distance, s. That's the distance from your starting point of your parametric. It doesn't really matter where it is, but it's a distance as measured from some starting point to along the curve to wherever you should happen to be at that time. And now I'm going to make an appeal. How curved is this curve? At this point, reasonable choice is, let's ask, how fast is this angle changing? Right, that angle, in a way, is kind of it's sort of defining the direction the curve is going, and I want to know how fast is that direction changing. If there's a lot of curvature, that angle phi is changing fast. If there's not much curvature, then that angle is not changing very fast. But now I do want to emphasize that I'm not interested in how fast phi is changing as a function of time. That's not what we're talking about. I want to distinguish again between the road and the road trip, right? I'm interested in how curved is the road. I don't care how fast you drove across the road. That's you personally, right? I'm interested in the road itself. So I don't want to know what is the rate of change of phi with respect to time. I want to know the rate of change of phi with respect to distance traveled along the road. That's intrinsic to the road. That make sense? We'll be looking for d phi ds. We're going to get at d phi ds by parametrizing, by taking a road trip, right? And we're going to compute d phi dt, and then we're going to try to figure out from that what d phi ds is. Okay. All right, so some of the objects that are going to come up in this little study will be the velocity vector. That's no surprise, I hope. That's our way of getting our foot in the door on direction, and we're going to eventually compute phi from that velocity vector. It's going to be interesting to talk about the unit tangent vector, capital T. This is going to actually be an important object of study in several different contexts, not just here in parametric curves. When we get into chapters 5 and 6, the unit tangent vector pointing in the direction of the velocity vector. Very important object of study. So that, of course, relates to the velocity vector. It's just the velocity vector divided by the speed. That's a flashback to chapter 1, right? Okay. So turns out, and this is a neat observation, after you've computed your curvature as rate of change of that with respect to that, you can take a different point of view on curvature. It turns out that if you look at this vector, which is the rate of change of t with respect to s, so how fast is that direction vector changing per unit distance traveled along the curve? It turns out, it's kind of surprising, but the magnitude of dt ds is equal to the curvature. Interesting, little quirky little fact. Okay. All right, so that's the two-dimensional calculation y'all will be working through. Now, I want to move on and consider now the three-dimensional version of this. We'll try to leave the two-dimensional version visible there. So we got a parametric curve. There's a velocity vector. The unit tangent vector pointing in that direction is going to be interesting and useful again. It's just that now that we're moving through R3, there's a whole separate direction that I have to worry about. And this is awkward. I'm just going to do a little bit of hand waving here. Let's suppose that I'm moving like this. Right? So I'm flying along, let's say, and I'm making a turn as I go to the left. Well, you could argue that the curvature of this path could be, you can get a sort of a hand on that by just thinking about the theta angle, the spherical theta angle, and asking how fast does that theta angle change. The problem is that's only meaningful and natural if you're moving entirely horizontally. What if you're moving vertically? Theta is not changing at all, and yet you're still curving. There's definitely some curvature in this sort of a motion, right? And then you think, okay, well, what about phi? Okay, well, yeah, but fine. What if you're curving like this? What if you're doing some sort of a weird banked turn in a plane like this, where you're turning somewhat to the left, but also somewhat up? Do you look at how fast phi is changing? Do you look at how fast theta is changing? Neither one really quite works, right? It's a bad way to think about curvature. There's two different directions to worry about, and therefore no single direction, such as indicated by this theta over here in the two-dimensional example, that can really work in that way for us. So what turns out to be super handy is to go back to the two-dimensional version and recall that, oh yeah, dt ds as a vector represented curvature. as it turned out. That was a little cute observation we made at the end. The good thing about it is that dTds is a perfectly natural thing to talk about in the three-dimensional context as well. Right? I can still talk about this unit tangent vector. I can still ask, per unit distance traveled along this curve, what's the derivative of that tangent vector, that unit tangent vector? And that's still naturally a vector. So curvature in the three-dimensional context is going to be defined as the magnitude of dTds. The way you're going to compute it involves a few other objects that come up. In particular, there is a vector called the principal unit normal vector that points in the direction of dTds. It's always perpendicular, as it turns out, to the unit tangent vector. These two vectors, n and t, are perpendicular, unit length, and therefore make a nice little reference frame for how to talk about various little vectors that are involved here. And the calculations y'all are going to go through are going to talk about how, using n and t, you can relate the acceleration vector and the velocity vector to help you compute dTds. So there's a bunch of different details in there, and that's going to be, again, a sequence of six or seven exercises that y'all will go through. So I just wanted to give you a brief laydown of what the objects in question were as you go through those problems. So you might want to re-listen to this portion of the lecture before you do those questions. Okay, so let me stop the recording here.